for ax. Oh, it froze again. That's awkward. Ax plus by equals c. Sure, 2x plus 2y equals? Someone give me another one. Sure, x plus y equals 1. Give me something with a negative slope. Oh, wait, those ones do have negative slopes. Give me something with a positive slope. Negative 3x plus y equals 4. Why is that a negative slope? Yeah. This one has a negative slope because you have to subtract the 2x to get to m. But Sam's negative 3x, you would add, oh, positive slope. Someone give me a whole number slope. Oh, wait, Sam just did. Someone give me a fractional slope. Oh, wait, you already did. What am I talking about? There are no fractions. But when you subtract the 2x, don't you have to divide by 2? Oh, that's a whole slope. Hold on, someone give me a fractional slope. X plus 2y, is that going to work? Because you subtract the x and divide it 2? Nice. Remember from standard slope-intercept form, to get the slope, you have to get y by itself. So you guys gave me a lot of different examples. Here's another question. Can someone give me a parallel line to this one? To this one. How did Gavin do that so quickly? He just doubled everything, right? But question, what would happen if you tried to solve this system? Because now we have two equations, don't we? What would happen if we tried to solve this system? Why not? They reduce to the same thing. If you divide this by everything, what's going to happen if you subtract this equation from that equation or that equation from this equation? 0 equals 0. Either you double this guy or you cut that guy in half, and aren't they the same thing? So when you subtract, it's poof. Well, hold on. 0 equals 0. Is that good or is that bad? It's bad because it's not like one answer, but isn't it also good because it's true? If it was false, what would that mean? No solutions. But if it's true, what does that mean? All solutions. So you guys didn't just, or Gavin didn't just give me a parallel line. He gave me the same line. Oh. No, but the same line is parallel, right? Which is good and all, but can someone give me a parallel line? Let me clarify, that's not the same line. How did Tony do that so quickly? They both equal 3, and guys, coefficients are different, but what? So, are they going to have the same slope? Yeah, subtract 2x, divide by 2, the slope is -1. Subtract the x, the slope is -1. They both have the same slope, but what's true now if you go to solve your system of equations? If you double and you subtract, you're going to get 0 equals, yeah, I think -3. Well, 3 or -3. You're going to get 0 equals 3 or -3. My question, true or false? So what does that mean about those two? Oh, hey, we haven't even talked about what the true-false thing is even indicating. So what do you find when you solve a system? If two lines that are the exact same have all solutions and two lines that are parallel, not the same, have no solutions, what are the solutions to a system of equations? Order pairs that signify what? If that's all and that's none, what are we looking for when we solve systems? Intersections. How many intersections if they're on top of each other? All. How many intersections if they're parallel and in a different place? None. What if we change the slope? 1. Is there any other way to get all, none, or 1? 1, 1, 1. None. 1. Ooh, we could do skew lines. We could have fun. That's geometry. Skew lines have none, but it's in different planes. Don't worry, we're not doing that. Okay. You guys remember the word skew, right? They're askew. Anyway. What are nonlinear systems? Because you're in pre-cal, we're not just going to stick with Algebra 1 stuff. It's totally Algebra 1 stuff. Nonlinear. Well, what if we have something like a, I don't know, 3x squared plus 2y is equal to 1. What is it now, a line? Nope. Standard form? Not really. Standard form of a quadratic would be y equals ax squared plus bx plus c, huh? Quadratic, could we have those? What if we had something even worse for our second equation of the nonlinear system? What if we had something like 5e to the x plus 1 equals 0? Now, could you algebraically put these two together by hand? The answer is no. So every now and then in homework, you might be given a system where you have non-like equations, like not even non-linear, but like they're not even the same. If they were both quadratics, I bet I could do something. If they're both e to the x's, I bet I could do something. If you have unlike equations, you're being sent to your calculator to find intersections. But as soon as you have curvy things, could you have more than one? Okay, so for linear, we're looking at all or none or one, if we're not like going different planes, which we're not. But nonlinear, we could be looking for more than one. Just remember, when you're solving systems of equations, you're looking for intersections, right? And we're going to be solving as many by hand as possible, which we can do with linear, which we can do with like nonlinear, or similar nonlinear equations. If they're both quadratics, go for it by hand. If they're both e to the x's, go for it by hand. If they're both trigonometric, go for it by hand. But if you have a quadratic with an exponential with a trigonometric with a cubic, you're not doing it by hand. You're solving using a calculator. Read the directions, but we should know how to do that. Right, guys? So, what if you were given something so basic it looks hard, you were given the directions, check the solution. Wait, what? They're not even telling you to solve it. They're just saying to check it. If they're saying check the solution, they're calling this guy a solution. If they're calling this guy a solution, what are they saying this guy is? An intersection. And how do we know if he's truly an intersection? Well, he has to be a point on him, and he has to be a point on him, right? So literally, Kyle was right when he said, don't you just, yeah. So some of the homework couldn't be that easy. Yep. Just remember to plug in everything the place or the spot where you're supposed to plug it in, right? AKA put your x's where your x go, put your y's where your y go. And all you got to do is give me a check mark at the end. Guys, if you plug in 2 and 1, does that actually end up being 5? All right, I know that is a point on that line, but we need it to be a point on that line to match. Easy cheesy, lemon squeezy. Patrick Sweezy. Just kidding, isn't that Swayze? Anyway, plugging in 2, plugging in 1. Good. If you rewrite it wrong, you might get in some trouble, but otherwise it should work. It was a minus. 6 minus 2 is 4. Check. Is it a solution? Yes. Well, that was a fun problem. Okay, homework's bound to get harder, and it does. But checking solutions, remember, they're intersections, and as soon as both equations in the system, or all 3, or 4, or 5, have a shared point, then we can say, yes, it's a solution. So, substitution. Why is it in green and not in blue? Aren't our notes usually in blue? Do you guys even notice my color coding? That's blue. That's blue. That's green. Green is review. Guess what? Almost all of section 7.1 is just review. Because have you seen substitution before? What does it mean? How would the book describe it? What? Do you need to write it all down? Not necessarily. However, in chapter 7, we are going to be talking somewhat about programming. Programming. What's programming? What requires programming? Yeah. Are computers kind of like a big thing this day and age? Oh. Are there people that have to know how to use said computers, program said computers, and work with said computers, and troubleshoot said computers? Create said computers? Yeah. Am I going to teach you how to do computer programming? No. Not my job. Not my specialty. However, as Mr. Moffat would say, you guys probably don't even know Mr. Moffat. He was an epic computer teacher here for years. He still comes in and helps Mrs. Christensen every now and then. But he would come into my classes when he was teaching AP Comp Sci, my pre-calc classes and my calculus classes, and he would be like, if you are in this class, you can program a computer. He's like, and I want you in my class. Why? Why would he come to the math classes specifically out of the entire campus and say, if you've made it to this level of math, you should come over and be in my class? Because the mathematical, systematic approach and analytical methods of tackling a problem and having a set formulaic way of dealing with the solutions are what can be very useful in computer programming. So, starting here at the very beginning with substitution, something so easy as plug it in. I'm going to show you, little by little, in some of these basic methods and then going into harder methods, systematic approaches, how you should be tackling these problems. And some of you are like, it's second nature to me. I don't really think about what I do and how I do it. Do you guys know there are college courses and majors that have all to do about thinking about thinking? But thinking is so basic, we just do it all day long, right? But there are people that have made it their life's career to think about your thinking and how you think and why you think and what that means if you think, right? Reasoning about reason. Gets pretty deep. Philosophy, logic. Anyway, so even though at some points this chapter, I'm just introducing it now, you're going to be like, why are we doing it this way? Because to program a computer, even though it does require creativity, it also requires systematic approaches of here is my end goal and how do I do steps 1, 2, 3, and 4 in order to get to that goal. Even so basic as if you were to, because there are so many different free intros to computer programming and AP Comp Sci and all that, or Comp Sci I should say, online. Like elementary kids are being taught the basics in some schools of coding, and it's not so much like, hey, let's start talking about like C+ or Java or these different like programming languages. It's like, how do you move this to here and give me a step-by-step approach? And it's like, oh, move the blocks down 1 over 3. Like that's their intro to programming. Just moving puzzle pieces or moving blocks on a screen. That's introductory programming, introductory coding. So we're way past that in some ways, as far as your mathematical, analytical thinking. So all that to say, plug it in. Why'd you give us a paragraph? Do I want you to memorize the paragraph? No, I just want you to think about your thinking. And some of you, your substitution's always perfect, and some of you, at some points this chapter, you will get stuck. So let's think about your thinking. Typically, when you have a system of equations, let's just say you only have 2. You guys know there can be 3 or 4 or 5, A, B, C, D. Ooh. Let's just say you have 2 equations. Let's even just say they're linear. What's the idea, the big idea, the generalization that totally encapsulates always using substitution, not just like in this one example, you're going to do this, but all the time. You choose one of the equations and you isolate one variable. Do you guys agree with that? So in the linear example we just did, you would choose an equation and either solve for x or solve for y. But to generalize that, to explain it in a way that encapsulates all examples, choose an equation, solve for one variable in terms of the other. Then what do? Solve for one variable, and then you substitute the expression back here. This is a systematic approach. Substitute the expression that you just got, but you have to substitute it where? Not in the same equation. You must substitute it into the other equation. And if you have an equation, substitute in all of them. Substitute the expression found in step 1 into the other equation to obtain an equation in one variable. Why? Well, if you only have 2 variables, if you just got rid of one in terms of the other, don't you now only have x's or now only have y's? Oh, life is so much better. Then solve the equation that you just got. Do you see how it's literally like a step-by-step of exactly what to do and how to use it? That's what you have to tell a computer. It doesn't have its own brain. I mean, kind of does, but computers aren't very creative on their own, right? Let's not go into AI right now. So, step-by-step of choose an equation, solve for a variable. Take that, plug it into the other equation. Solve that equation, the result. Number 4 says, ooh, new word. Can you at least make sure to write this new word down? I'm going to use it quite a bit this chapter. What's the new word? Back substitute. But what does it mean? It's very basic. Go back and plug in, right? Back substitute. Solve the equation. At this point, you either have an x equals or a y equals, true? Now, for a computer, you probably wouldn't let it choose. You would say, you can work, and you can work really, really quickly and really, really efficiently. So I'm going to tell you every time, solve for y, plug in, then solve for x, because otherwise the computer making a choice isn't a good idea. So even though we would say, in this one, let's solve for y, in this one, let's solve for x, and this one, I don't want to solve for either. You are creative, and we have to choose. We wouldn't tell the computer that. We would say, no, definitely, just go for one, plug in, solve for the other. I don't care if it's messy. Can your computer, can your calculator give you messy answers? Do you feel bad for it when it gives you decimals? No, you're like, whatever, you're a computer. Exactly. Okay, go back, plug in, and find the other. If you have x equals 2, can't you go back and plug in x and solve for y? But strategically, where would be the best place to plug it in? At the very, very beginning when all the equations are like with x's and y's and all mixed up? No. Where would you want to plug it in? Yeah, you would want to go plug it in step 1 because this one already has y equals in terms of x. Yay, I found x. Or x equals in terms of y. Yay, I found y. That's the place you'd want to plug it in. And then number 5 just says, check that it satisfies each. What are we looking out for? Extraneous. Now, are there ever going to be extraneous solutions in linear equations? No. Why? Because lines don't have restricted domains. Where have extraneous solutions shown up this year? What has restricted domains? Logarithms. That's the first place we saw it. Because logarithms, remember, there are all these numbers that are illegal in a log. And if we are solving mathematically, we might not see, when we take out the log, that an answer that snuck in might be illegal. So this last step shouldn't be a big deal for linear unless subtraction, multiplication, division, which we all can do, right? So checking is always a good idea. How do you check? What we just did. Plug it in, make sure it works. Down here. For our purposes, because we're not computers, it's totally valid to be like, hey, in step number 1, just solve for the easiest one, because you guys have brains. You can actually look at it and say, oh, I think it's easier to solve for x. Oh, I think it's easier to solve for y. A computer, though, we wouldn't feel sympathetic. We wouldn't care. Ready? Set? Wait, what? It's a system. Go. But there's a log. Too bad. I'm telling you, you can do it by hand. Go. If you guys notice, the log only has an x. It makes it a little bit easier. Since you guys have brains and you aren't computers, I need to ask you some questions right now because you're making choices. Crazy. Computers can't really make choices. Humans can. You're making choices. What are you choosing, the first equation or the second? Cool. What are you solving for? Okay. Now, some of you are choosing the first and you're solving for x or you're solving for y. You got to make your choice. So once you have your choice, keep it. But for my purposes, I think this is the easiest one to solve for because what can we do if we solve for x? Can't we find them right away? What does x end up equaling? Don't say 30. Don't say 13. Say 1,000. 10 to the power of 3, right? Why did you need to start with the second? And, yeah, the bottom one only has one variable, so you can solve for his value and then plug in to the two variables. Everything gets harder when both of them have two unknowns. But whenever you have only one unknown, your brain, hopefully to some extent, when reminded, will start exactly there. We have 1,000, go ahead and plug it in. What happens if we plug in? We back substitute? No, we're just substituting. We solve for x, we got 1,000. We're not back substituting, we're just plugging into the other equation. We get 1,000 plus y is equal to 2. Anybody square both sides yet? Then when you square both sides, I ran out of room. Lo siento. Should have rewritten the order. You end up with? No, plus or minus is only when we're square rooting and getting an absolute value. So since we're just squaring to get rid of the square root, we have just a positive 4. So therefore, y is equal to negative 996 when you subtract 2,000 from both sides. How could you write this as an ordered pair? Yeah. Why would you not have wanted to go to your calculator on this one? Wouldn't you have had to zoom out, zoom out, zoom out, zoom out, zoom out to find that puppy? That's way beyond our little 10 by 10 standard viewing window. You could have found it in your calculator, but man, it was a lot easier to do by hand. You guys agree? Cool. How do we solve this guy with substitution? Oh, this looks more normal. Oh, one's a line and one's not. Can we use elimination? You guys have brains. Who should you solve for? Do you guys see why that's the easiest? Because don't we just have to go ahead and move that guy to the other side? But is it the easiest? What are we going to have to do? Oh, look at all those fractions. Did your brain lead you in the right direction? You can do that, and it would be fine. But why am I going to say we should solve for him? What happens when we solve for x? Aren't my fractions going to be a lot nicer? Meaning, aren't I not going to have fractions? Because x is equal to a positive 2y plus 5. Does that look nicer? I think so. But you have a choice, and sometimes your choices lead you to messier situations, and sometimes they lead you to nicer situations. There's a life lesson in that. Doesn't mean your choices were necessarily wrong. Sometimes it's just the way the cookie crumbles. But in this case, maybe it's an advancement of your abilities if you don't always just solve for what's the easiest as far as right in the immediate, but you look to the future. So many life lessons. You think ahead and you're like, ooh, I don't think I want those fractions. Or you have the courage to reevaluate and say, I think I could have chosen better. Let's try again. Okay, now that I have this expression, what am I doing? I pick an equation. I solve for one. I substitute it into the other. This is our system. It will work every time if we follow it. As long as we keep the math legal. You guys see me plug it into the other solution? Or the other system, the other equation? Yeah. Yep. Don't kill a puppy. We're going to end up with 4y squared. Plus 10 is plus 20y. Plus 25 plus y squared equals 25. Why would this problem never be in Algebra 1? Because it requires your guys' skills to keep going. But the substitution basic idea was introduced. Would you guys have combined 4y squared and 5y squared? Plus 20y. Hey, what happens when we get everything to one side because it's a quadratic, though? Nice. So 5y times y plus 4. Y equals, there can be more than 1? Because you had a curve. And you didn't just have a quadratic, you guys had a circle. Look at the graph. The graph tells you how many different intersections should you have? 2. When y equals 0 and when y equals -4, what do we do once we get one variable completely solved for? Back substitute. Where? In the nice little spot waiting for him. So I can go ahead and take 0 and 4 and say, all right, it's time to go back. It's a life lesson in that too, but that's okay. X is equal to, we could say x of y is 0 if you want to use function notation, and x of -4. Plugging in 0 for y, you get 5. Plugging in -4 for y, check me, is that -3? So you end up with 2 different solution points. They say to double check your math with your, there we go, I don't know why it took me so long, with your graph. And to be honest, some of you might realize it might have been harder to graph this guy and find the intersections than just to do the math. The final solutions for number 11, or for this first one, are -3, -4, and 5, 0. Okay, how about the example at the bottom of the page, though? Oh, they're both lines. Do you guys see it? So since they're both lines, the answers are either all or none or 1, and who is he? What would you guys think of doing? That's no fun. Why? It's linear. This is an Algebra 1 problem. You guys scare me sometimes. How would you solve them? Oh, you haven't learned this by now? You haven't had teachers that love you enough to tell you, or you haven't been loving yourselves enough to remember? Couldn't we multiply everybody by 4? Why is that nicer? Because wouldn't you then have 2x plus 3y is equal to 40? Because the 4 goes to everybody and some fractions go away. It's kind of like my Uganda complex fraction trick. I don't know the multiplying top and bottom by the little baby stuck denominator. Never mind. We'll get back to that someday. On the bottom, 3x minus 3y equals 16. Do you like him more?
Oh, much more.
Much more. You're going to cheat just a little bit and use something called elimination? Why? Because you have brains, and you've seen multiple ways of solving this before. That's why in many ways you're better than a computer, besides your personality, your gifts, your talents, etc. But your hearts. 5x is equal to 56. It is a fraction, but are we super scared of it? No, because it could have been a whole lot worse a whole lot earlier if we'd say solve for y, which is what 1 would tell you to do. That'd be nasty fraction nastiness. Did I do something wrong, Adam?
Well, you multiply 4 by -y, but then up there it's -3.
Oh, instead of -4. Oh, did that just make everything harder? Maybe the answer is nicer than we thought then. Why? Well, I can't exactly just do that though, can I? Equals 3x minus 4y. Ah, what are we going to have to do for elimination? You know what I would have done? No. I probably would have come over here and not been too frightened of things. And I probably would have taken this guy. And I would have solved but for y equals. Because if you guys noticed, if I moved him and multiplied everybody by 4, maybe it wouldn't have been that nasty anyway. But in some way, shape, or form, do you guys know how to do elimination on this guy? You should. What would you get rid of, the x's or the y's? I see the positive, negative. I like. Is this a thing that you've done before? And then you add it all together? So what else is there in homework, really? Well, there are questions that say, use your calculator, use your graph. What does that mean? Find the intersections. Can you use your calculator? Find the intersections. Kiddo, 7.1 due tomorrow. See you guys later. Bye. Gracias, Chapo. Adios. Bring homework questions tomorrow in case you get stuck, but I think we'll be all right. Have your graphing calculators tonight, for sure. For sure? All right.
This one has no name on it.
On the top?
On the top.
Okay. Thank you, Rachel.